Hi, this is Andrew Livingston. Again, this is a recap of what happened in the lecture for CTR08108, week 6. We're looking at variability of material properties, a recap and further strengthening on what we had in week 5, and then looking at BSEN 408, this is the test procedure for strength and stiffness perpendicular to grain, and we'll also look at bending strength as well. Move over to the slides. And okay, a recap on last week. Engineering materials are inherently variable, and we talk about that and we catalog it by calculating the standard deviation. This is a notation of how we calculate the standard deviation. We get the average, we get the variance, then we get the standard deviation from that. And again, these are the properties here that we'll be determining within all of these tests that we'll be doing within the practical session. Compressive, strength parallel to grain, and then perpendicular to grain, and then modulus of elasticity or the stiffness, parallel to grain, and then orthogonal or perpendicular to grain, and then we have the bending strength. So last week's lecture, we had the compressive strength parallel to grain, and then the modulus of elasticity parallel to grain. So that's FC0 and EC0, all in accordance with BSEN 408. But now we're going to look at the perpendicular to that. How do we derive FC90 and EC90, and also the bending from the 4-point bending test? Determining the modulus of elasticity perpendicular to grain for structural, i.e. solid timber, not GLT or glowing laminated timber, seen on page 27 of BSEN 408. You can see the grain directions going in a different direction to the load being applied. H is the height here, breadth and length. So the area would be breadth times length. Now, for the sample that we'll be testing, it has to comply with the dimension samples, as we'll be using height being 90 mm, breadth being 45, and length being 70. So the clause, so that's clause 17.1 for the dimension of the samples. The modulus of elasticity shall be determined from the equation in clause 17.31, which is EC90 equals F40 minus F10, all multiplied by H, and then all of that divided by W40 take away W10 multiplied by the area, or BL, where F40 and F10 are quite simply, this time, 10% of F max and 40% of F max, where last week it was approximate. For this week, for it perpendicular to grain, it has to be 40 and 10%, not approximately but exactly. So the question would be, what is F max? We can see in this graph that F max is it's not a random point, but just now it may appear to be some random point on this curve. Unlike the compression parallel test, the F max is not the highest point on the curve. It's on the curve, but it's not the highest point on the curve. So then, how do we find the F max? Okay. We're going to use the following iterative procedure, which essentially means we do it and we then do it multiple times until we get it good enough. And we'll talk about that. Pick a point from the curve and read the corresponding force value. This is your initial guess for F max. So let's call that F max guess, or guess 1, I suppose. Then calculate 10% and then 40% and determine where these two values intersect the load deformation curve. And then through these 2 points, we draw a straight line, either by hand or by using the equations given the 2 points. We translate this line so that it intersects the horizontal axis. So we translate this line so that it intersects the horizontal axis at, W equals 0.01 times h, and h is this height. So we're going to move this line across horizontally a particular distance, 0.01 times h. So if you were in my tutorial session last week, you would have seen these equations already, or from high school, I suppose. Equation of a standard straight line, where c is the intercept where the line crosses the y-axis. Then same equation of a straight line, but with the x-intercept. There's also a link there where I'm getting that from. Okay. What value to consider? Blah, blah, blah. Right. Now we're down here. If the value for C max, so determined, is within 5% of the C max guess. There's my C max guess, and there's my actual C max. If it's within 5%, then we're all good. If it's not within 5%, then we go back and we have another go at picking where the Fmax guess would be. In this scenario, you would move it slightly further up. You wouldn't necessarily go all the way up to there, but you could go part way in between and then do the procedures again, and hopefully you are within the correct percentage. So this is our sample again, the same test, and we're now going to look at the strength perpendicular to grain, which is FC90, which is essentially the exact same as you had before, just the notation is different. FC0 is now FC90, FC90 max. Now just for clarity, this intersect on that line here, this is the FC max. Don't use this value here. That's just your guess. So this is the value you'd want to use, only if it's within 5% of each other. Okay. And very straightforward. I will demo how to do this in the tutorial sessions. Unfortunately, I can't record the demo tutorial sessions. So please try and make sure you're at these Excel tutorial sessions if you can. Okay, now for the last coursework, which is the bending, 4-point bending test, we'll look at this. Determination of the bending strength, FM, see page 32 of BSEN 408. How do we apply a bending moment to measure the bending strength? Quite simply, we're going to apply what's called a 4-point bending test. If you were with us last year, you'll have seen a thing called a 3-point bending test on the concrete. But for this type of material and for what we're going to be doing here, it would be a 4-point bending test. It would be applied something like this. We're pushing down, simply supported beam, and we're going to get a bending happening in this member. So if the force divided by 2 is applied at distance A in from either side, then what we're going to get is a bending moment happening around where F2 is. Oh, sorry. Okay, so therefore we would have the moment would equal the force divided by 2 multiplied that by that distance A. And that is just the distance from here to here. And so according to figure 17 of BSEN 408, this is the criteria that we have. The length of, or the supports, should be 18 times h. H is the height of the member, and h should equal the breadth as well, I may add. And there's a tolerance factor of plus or minus 3 times h. And then we have A, which is 6 times h with a tolerance of 1.5 times h. And obviously this section here and this section here would have to be the same. We couldn't have that, being different from each other. And the middle section is just 6 times h. And then, quite simply, we will have Fm equals 3 times Fmax times A, all divided by breadth times height squared. That then gives you the Fm, or the bending strength of that timber. Now, in the tutorial session, so the lab session, please make sure you take lots of photos, not just of the test, but anything and everything that is used within the lab for these tests, and make sure you understand what it is you're writing up. I would also say, please make sure that you can attend my tutorial sessions on Microsoft Excel. It will be an invaluable help. And we'll be giving you the test data in what's called a Microsoft Excel file format. Okay, that is just a very quick snapshot of what we've been talking about in class. For those that couldn't make it, or for those who need a bit of revision afterwards. Thank you very much, and I'll catch you next time.